So hello everyone. So in this presentation, I'm going to present you a methodology which aims at proposing an optimized sensor siting for offshore wind resource assessment. So the context is the following. For a given area, what would be the optimal number of wind measurement systems to be deployed within an area? And where should we deploy this sensor? As wind measurement system, I refer, for example, to floating LiDAR, which is a certified instrument for offshore wind resource assessment. So, for example, you can see the floating LiDAR accuracy here. So we developed our methodology over 3 regions that are related to the ongoing and next call for tenders in France. The first region is off the coast of Normandy. The second is off the coast of southern Brittany, and the last region is an area in the Mediterranean Sea. The dataset used to develop the methodology is a MeteoNet dataset made publicly available by Météo France. This dataset is composed of output of numerical weather prediction model AROM. There is a horizontal and meridional wind velocity at 10 meters. This is a 3 years long dataset, and the zonal and meridional velocities are distributed on a regular grid of 1.3 kilometer spacing. So the MeteoNet dataset covers 2 large areas, shown in red in the right-hand side figure. From these 2 large areas, we extracted 3 sub-regions already mentioned. And here I provide the characteristic of each area in terms of number of grid points and surface. So this characteristic does not consider grid points at land. We developed the methodology by considering only the grid points at sea. Our methodology is based on the data classification method called Gaussian mixture model. The Gaussian model is composed of Gaussian distribution of some d-dimensional vector x, characterized by its mean and its covariance. X has a density f, whose mathematical expression is known, I guess, by all of you, so we won't spend too much time on that. And the Gaussian mixture model is composed of k Gaussian distribution with a respective density function f1 until fk, where each distribution is associated with its mean and its covariance, and the density p of x is thus a sum of the distribution f. So here is an example based on the one-dimensional dataset. The dataset is decomposed into, for example, three clusters. Each cluster has its own Gaussian distribution. A Gaussian mixture model requires to set as input the number of clusters for which we want to decompose our dataset. So for this purpose, we calculated the Bayesian information criterion, the big score. The big score is a criterion that gives an estimation on how much is good our Gaussian mixture model. For the lower is the big, the better is the model. We are looking for the minimum value of the big score. So the big score considers the number of data points, the likelihood, and the number of free parameters, which is the number of clusters. So we can see from the mathematical expression of the big score that this score is penalizing the model with a too large number of data points. So the Gaussian mixture model requires as input a 2-dimensional data set. So at this stage, we have a 3-dimensional data set, so 2 spatial dimensions and 1 temporal dimension. And we need to reduce the dimension of our data set. So to do so, we employ an empirical orthogonal function decomposition, EOF, also called the principal component analysis. So the first EOF is representing the most dominant spatial mode of our system. The second is representing the second most dominant spatial mode of our system, and so on. So we calculated the EOF for the meridional and the zonal velocity. We decided to restrict the analysis to only the 10 first EOF, which explain more than 97 and 98% of the variability, depending on the study area. From each EOF, we then decompose the 2D area into a 1D vector by doing a reshape. So we get a dataset composed for the Mediterranean Sea of more than 3,571 grid points by 20 features. So this is our input. Our output is a one-dimensional vector where each grid point is associated with a label that identifies the cluster of belonging. So then we reshape from one-dimensional to two-dimensional to create such map. So here's an example for decomposition into 5 clusters. As I said earlier, another input of the Gaussian mixture model is the number of clusters we want to classify our dataset. So to determine this number, we calculated the big score and represents the gradient actually of the big score, which is easier with this representation to identify a clear asymptote. And what we are looking for here is an elbow in the curve. So this is a clear change of slope. So we can see in the figure that an elbow is identified for a number of clusters equal to 5 for the Mediterranean Sea. So this is the optimal number of clusters. So it does not change when we add more EOF, which justify our choice to feed a Gaussian mixture model with only 10 first EOF. So the dataset is thus lighter, so easier to handle. And the optimal number of clusters for the Normandy and southern Brittany was found to be 4. And we do not restrict, however, our analysis to the only scenario associated with the optimal number of clusters. We investigated other scenarios with a number of clusters ranging from 1 to 10. So here's what we obtained for the Mediterranean Sea area. So once we identify our cluster, we then need to identify the optimal location of each sensor within each cluster. So we consider in this analysis that one cluster is associated with one sensor. So the optimal sensor location, so the red cross in the right-hand side figure, so the optimal sensor location within each cluster have been set to be the grid point with the maximum likelihood. The likelihood is another output of the Gaussian mixture model. So this point is most likely to belong to the cluster and is the most representative point of the cluster in terms of wind characteristics. So once we have the optimal location, we calculated the correlation between 3 years long time series of the velocity magnitude at the optimal location between 3 years long time series of the velocity magnitude associated with all other grid points. So here's an example for a scenario composed of 3 sensors in the Mediterranean Sea. So we calculated the correlation for each sensor independently, and then we combine all correlation maps. And for each grid point, we selected the maximum correlation so as to generate such map on the right-hand side figure, which is a maximum correlation of the velocity magnitude, that is which for a network composed of 3 sensors in the Mediterranean Sea. So here with this work and this slide, we wanted to demonstrate that the number of clusters determined by the big score is equal to the number of sensors we need. So this was an hypothesis I mentioned at the beginning of the presentation. So to test this hypothesis, we calculated the number of grid points where the correlation is higher than 0.95 for different number of sensors. We obtained the following curve for each study area. So note that the trend here was the same for correlation set to 0.9 and 0.99. So here we are looking for again for an elbow, so clear change of slope. So this an elbow would mean that the addition of more sensors would not bring significant additional information in terms of wind characteristics. So you can see that it's on the left-hand side figures that it's not easy to identify an elbow with the correlation. However, for the Mediterranean Sea, it seems that there is a change of slope at a number of clusters of 6, for the Normandy 4, and for the southern Brittany 4 or 5. So this is more or less actually what have been estimated by the big score. So we can consider that the optimum sensor required for for calculating the wind, the offshore wind would be estimated by the big score. And with the gradient of the big score, actually, it's easier because we have a clear identification of an elbow for each area. So 5, 4, and 4. So here are the optimal sensor network for each region investigated. So in the Mediterranean Sea region, the deployment of 4 sensors will allow to cover on average 1,200 km² per sensor. In the Normandy region, we will need 4 sensors that will cover on average a surface of 1,750 km². And finally, in the Southern Brittany region, we will need 4 sensors. Each sensor will cover on average 750 km². So with such sensor network, 34% of the area has a correlation higher than 0.94 in the Mediterranean Sea, 44% of the area of the Normandy region, for the Normandy region, and more than half of the area on the Southern Brittany. So if we want the correlation of 0.95 in more than half of the region for each study area, we would need to add 4 more sensors in the Mediterranean Sea and 2 more sensors in the Normandy region, which will give an alternative sensor network like this one. So net sensor network composed of 9 sensors in the Mediterranean Sea, 6 sensors in the Normandy region, and for the Southern Brittany region, it does change. So the conclusion of this presentation, so we can answer the question of the introduction. So for a given area, the optimal number of sensors can be found by the calculation of the big score. And the answer of the second question would be the optimal sensor sighting within each cluster can be given by the location of the breakpoint with the maximum likelihood. And as a perspective, so further work on this topic would be done by considering other dimensional reduction, comparison with a given certain metric, for example, a width field reconstruction across the entire map. So, for example, with a support vector machine or CNNs or network. With a CNN, neural network. So this is some work we are doing actually with Robin Marcy, which is a PhD student at France Energy Marine, and we are working on this specific topic. Thank you for your attention.